Alright, problem 28 in group theory. Prove that the intersection of two finite index subgroups of a group G has finite index in G. And I'm going to be using this theorem below, the criterion for left cosets, which says that if you have two left cosets, they're equal if and only if we have this relationship, where the inverse of the first element times the other element is in that subgroup of your original group. Okay, yeah, I suppose I'm not saying here, but these are cosets, left cosets of H, which is a subgroup of G. All right, let's set up the problem. So we're going to prove this problem by defining a map. So let's first set up what they have. We want two finite index subgroups of G. So let H and K be subgroups of G such that the index of H in G is finite, and the index of K in G is also finite. Okay, so we have two subgroups of G that have finite index in G. Define phi from G modded out with, this is where we want the intersection of the two finite index subgroups. Right arrow. Okay, and then we're going to go G modded out with H cross G modded out with K. Text. Defined by, let's see, you want phi of a left coset of H intersect K to map to GH, comma GK. Okay. And because we're introducing a map, we're going to prove two things. We're going to prove that first it's well-defined, so we have a well-defined map, and then we will show that it's injective, because if we consider orders, well, if it's injective, the order of this is less than or equal to the order of this, and we know that the order of G modded out with H is just n, and the order of G modded out with K is m, which are finite. So we have the product of two finite groups, which is finite, and this is less than or equal to something that's finite. Hence, this is finite index, which is what we want to prove. Okay, so we're going to start with injective. We claim that phi, sorry, not injective. We claim that phi is well-defined. So to show something is well-defined, you suppose that we're going to suppose that this is equal to G prime. That's what I meant to do. Oops, can't spell cap. So we have two of these are equal. And we want to show that essentially GH GK is equal to G prime H G prime K. Okay. So since we have this relationship, we can kind of multiply by G inverse on both sides, and this gives us, so let's say that by multiplying by G inverse on the left, we get G inverse G prime times this intersection is equal to the intersection. Okay, and we're going to think about this claim a little bit. Okay, so we have this relationship. So we have that G inverse G prime is in the intersection. Okay. So we have that G inverse G prime is in the intersection, hence G inverse G prime is in H. And so by the criterion for left cosets, we can say that G prime H is equal to GH. We can do the exact same logic with K. We have that it's in the intersection of H and K, so we can just say that it's in K. But I'm just going to say similarly, we have that GK is equal to G prime K. And so GH comma GK is equal to G prime H comma G prime K. Thus, phi is well defined. Okay, so we have well-definedness where we use the criterion for left cosets. Now we want injective. Moreover, we claim that phi is injective. To that end, suppose that, okay, we want two elements that are equal, so GH, GK is equal to G prime H, G prime K. So this is kind of like going the other way. We're showing that two of the images are equal to the kind of pre-images. Okay, let's see how this looks. Okay, so we have that GH is equal to G prime H. To that end, suppose that we have two elements that are equal, two images that are equal. Okay, and because this is component-wise, we have that GH is equal to G prime H. Hence, well, we do what we did before. Multiply on the left by G inverse, we get G inverse G prime is in H. And similarly, we can do the same thing with K. Similarly, we have that G inverse G prime is in K. Thus, G inverse G prime is in H intersect K. And by the criterion for left cosets, we have that pretty much exactly what we want. We have that G H intersect K is equal to G prime H intersect K. Therefore, we have that phi is injective. Okay. Consider orders now. All right, let's see. We have the order of G modded out with H intersect K. Let's put that in parentheses. And, well, this is equal to the index of H intersect K in G. Okay, but because this is injective, this is less than or equal to the order of G modded out with H, we said earlier, is just the index of H and G, and similarly with K, which we know to be a finite amount. It's n times m. Okay, so we have that the intersection of two subgroups with finite index have a finite index themselves. Okay. So let's just spell that out. Therefore, the intersection of two finite index subgroups of a group G has finite index in G. And we are finished with 28.